Welcome back, Johnny. Glad to have you with us today for third day of coming in at lunch to catch up on what you missed. Man, you missed so much material, didn't you? For sure. Well, the past couple of days we were examining the mole, and I was telling you about, how it's a really huge number, and you can perform any different calculations within chemistry and conversions just from knowing the amount of moles element or compound has. And then I worked through some basic example problems, primarily doing unit conversions, but also working with percent composition calculations as well as empirical formulas. Now, in today's unit, we're going to be looking at applying the mole concept to chemical reactions. And basically what this unit is called is stoichiometry. Now let me just say that names in chemistry can be really weird sometimes because at first when I heard it, I'm like, what? Stoichiometry. I know, it's very long. Essentially the term comes from the ancient Greek words stoichion, which means element, and metron, which means measure. So it's basically measuring elements. Well, in this case, it's actually measuring the amount of moles or grams in different chemical reactions. I remember one time when I was in high school, I remember when I had a stoichiometry test, I'm like, you know what the hardest question on a stoichiometry test would be? Spelling the word stoichiometry. It's absolutely like a strange word. It's very long and hard to spell, so I remember always joking around with that. But that goes to show you that it's actually not that hard a unit. Basically, if you know what you're doing with the mole, it should not be too difficult because it's just taking the mole and going maybe a little bit further. But for this unit, spelling the word stoichiometry is probably the hardest question. I'm not even kidding. Anyways, let's get this started. So in yesterday's lesson, Johnny, you learned about doing different conversions. Well, stoichiometry is essentially the same thing. However, there are some important things you need to know. So, just to give some background, stoichiometry is the relationship between the amount of chemicals in a reaction. This relationship allows us to predict the amount of products produced in a reaction or the amount of reactants needed for a reaction. Calculations can be done provided we have a balanced chemical equation, because if we do not have a balanced chemical equation, then we will not truly know the amount of atoms for a particular element or compound in a reaction. So the first one, the equation is balanced, as noted right there in point A. And B, moles are used to go from one chemical to another using the mole ratio, which is essentially what we did last lesson, Johnny. So as long as those two things are there, you are able to determine amounts of like moles or grams, etc. So for this first question, what do we need? Well, let's look at this. What do we need in order for a calculation to be done? A balanced chemical equation. Okay, so let's look at this. So we got sodium chloride. Oh, my pen's not working too well. Sodium chloride, right? And we're produced from 10 moles of chloride gas mixed with excess sodium. So chlorine is actually diatomic. So that means that chlorine by itself, it bonds specially with itself. And when we refer to chlorine as an element, we always just refer to it as Cl2. It's one of 7 diatomic elements. That's in different units, but just know Cl2. Chlorine gas is Cl2. Okay, so we have Cl2 mixing with excess sodium. Sodium is not diatomic, so it'll just be Na. And this will produce sodium chloride, which is NaCl. Wait, that's not balanced. There's 2 chlorines there and 1 chlorine there. Ah, very smart. So we need to put a 2 here to balance those chlorines. Oh, Now there's 2 sodiums and 1 sodium there. Let's put a 2 there for the Na. And there we have our balanced chemical equation. Right there. Okay. So next we need to, so just like in the mole concept, we start with what we're given. We're given 10.0 moles of Cl2. 10.0 mole Cl2. What do we want to convert these moles to? Let me think. Maybe, if we're trying to figure out sodium chloride grams, maybe we can convert moles of Cl2 to moles of sodium chloride. Exactly right. That's how you do it. When you have a balanced equation, what this is telling you is that for every mole of chlorine gas, there's 2 moles of sodium chloride, because there's a coefficient of 2 there, but there's a coefficient, this is technically 1. It's not written, but it's just assumed to be 1. And that's what the mole is. So in a balanced chemical equation, for every 1 mole of chlorine, there will be 2 moles of sodium and 2 moles of sodium chloride. So we can take this amount and convert that to moles of sodium chloride. So let's do that right now. So let's multiply that by 1 mole of Cl2 per 2 moles of NaCl. Those units will cancel out, and that'll give us moles of sodium chloride. But now we also need to figure out, so now we have the moles of sodium chloride, and now we want to figure out how many grams can be produced. So just like in moles, you want to figure out molar mass. Molar mass of sodium is 23, and for chlorine it is 35.5. And NaCl, there's 1 of each, so we can just add these up simply, and that should give you 58.5 grams per mole. 58.5 grams per mole. So we have moles of sodium chloride. We're converting to grams, so we know it takes 58.5 grams of NaCl to make 1 mole of NaCl. These units will cancel out, and that will leave us with the amount of grams of sodium chloride that we have. So let's perform this calculation into our calculators and see what this gives us. Let's see here, 50. Okay, that should leave us with that, and that gives us 1,170. So that will give us 1,170 grams of NaCl. Can be produced from that amount of chlorine. That is the final answer. Again, significant figures could be addressed here. Technically, we start with 3 there. Actually, technically there is 3 there because zeros are non-significant. But in this case, because there's a decimal there, both of those would be significant. So actually that would be technically correct. So yeah, that's really all it is. That's the idea behind stoichiometry. When you have a given amount of one element or compound in a reaction, and you're trying to figure out the amount of a different element or compound in the reaction. Now, let's go to question number 2. Question number 2. Now, 1 volume of oxygen is needed to react with 27.5 liters of hydrogen if both gases are at the same temperature and pressure. So, Avogadro, the person who actually the mole concept is named after, so 6.022 times 10 to the power of 23 is named Avogadro's number. So, he was a chemist a couple hundred years ago, and he has a hypothesis that says equal volumes of all gases at the same temperature and pressure contain equal numbers of particles. So this allows us to to solve these types of questions quite easily, because we know that if these gases are at the same temperature and pressure, they're going to have the same amount of particles, which allows us to use the mole ratio to solve it. If they didn't, it would be very, very tricky to solve it, but knowing that, we are able to just use the mole ratio to solve that question. So, once again, what do we do, Johnny, to first solve this question? Well, I think we have to write a balanced equation first. Yes, very good. So we got oxygen needed to react with hydrogen, and that's it. So oxygen and hydrogen are both diatomic elements. There are 7 diatomic elements. Actually, I'll just tell you them right now, just so that you know. And diatomic, like I said earlier, is basically you write an element and it has 2 next to it. Non-diatomic elements will just be on its own. So the 7 diatomic elements are hydrogen, iodine, bromine, chlorine, fluorine, oxygen, and nitrogen. Those are those diatomic elements. So we have O2 reacting with H2, because they're both diatomic elements. And what will this give us? It should be pretty obvious. It will give us H2O. That gives us water, because we have hydrogen as well as oxygen. But, of course, this isn't quite balanced yet, because we got 2 oxygens here and 1 oxygen there. So let's put a 2 in front of this H2O. Oh, now we have 4 hydrogens. Let's put a 2 right in front of that H2. And that's it. Okay, so with this question, once again, we're going to assume STP, which I mentioned in the previous lesson, is 22.7 liters, which will be used later in the question. So we start with 27.5 liters of hydrogen, because we write down what we start with. Now we can actually convert this to moles of hydrogen, right? So we know 22.7 liters is 1 mole, as mentioned in the previous lesson. 22.7 liters, I didn't write that too well, of H2 for 1 mole of H2. And that'll give us moles of hydrogen. Those units will cancel out. That'll give us moles of hydrogen. Now, just like in the last question, we can take this chemical equation, the balanced one, and go from one element in the reaction to another. So for every, because we're trying to figure out the volume of oxygen needed. So if we look at the balanced chemical equation, we know that 1 mole of oxygen is needed for 2 moles of hydrogen that reacts. So we're going to put 2 moles of H2 in this denominator, and then 1 mole of O2 in the numerator. And that will give us moles of oxygen. And now, once again, we can use STP again. 22.7 liters for 1 mole. So 22.7 liters of O2 for 1 mole of O2. And those units will cancel out once again. And then if we type that into our calculator, that should give us 13.75 liters. 13.75 liters of O2. So that's the key with stoichiometry. It's simply a relationship between amount of chemicals in reaction. When we have a balanced equation, we know that that the amount of moles of one substance in an equation is directly related to moles of another substance in an equation. That's what always that middle concept is, and that goes back to point B. Calculations are able to be done provided we have a balanced equation as well as moles being used to go from one chemical to another. Question 3. A reaction contains 60 milliliters of 0.200 molar sulfuric acid. What is the mass amount of magnesium metal that will react with sulfuric acid? So the M, you may or may not be familiar with it. It simply means molarity, which is essentially the moles per liter. Molarity equals moles per liter. And it's essentially referring to concentration of something. So if it's 0.200 M, that means there's going to be 0.2 moles for every liter of substance. That's essentially what that means. 0.2. Yeah. Okay, so let's start once again. We have to write a balanced equation. So let's write this out. So we have magnesium metal, not diatomic, reacting with sulfuric acid, which is H2SO4. And that will give us, what will this give us? Well, this is an acid metal reaction, which produces hydrogen gas and a salt. You might know that from prior knowledge, but that's basically what happens in an acid metal reaction. So this will give us hydrogen gas plus a salt. Mg combines with SO4 to produce magnesium sulfate, which will be MgSO4. Is this balanced? It actually is. This is balanced. We don't have to add any more coefficients, which is convenient. So we start with 60 milliliters of sulfuric acid. Now, since we want to be using liters in this case because molarity refers to moles per liter, we want to convert that milliliters to liters. We know 1,000 milliliters is in a liter, so we can divide 1,000 by 60 to get 0.06 liters. So that will give us 0.06 liters of H2SO4. So now we're going to take this liters and convert it to moles of H2SO4. Now looking at this, 0.2 moles per liter. So we know that 1 liter of H2SO4 is 0.2 moles of H2SO4. Those units will cancel out. That'll give us moles of H2SO4. Now, since this is already balanced, all the coefficients are 1, we know that 1 mole of H2SO4 is reacting with 1 mole of magnesium, but we can still write it out anyways, just so that it's correct. 1 mole H2SO4 reacts with 1 mole of Mg, and this is because all the coefficients are 1. And then what's the atomic mass of magnesium? That is 24.3 grams per mole. So we have moles of magnesium right now, and we're convert that to atomic mass. So we have 1 mole of magnesium for every 24.3 grams of Mg. Those units will cancel. When we type this into our calculator, we should get 0.292 grams of Mg. That is reacting if we have that concentration. So, as I said before, when you see that M, the capital M, it refers to concentration, which is moles per liter. Right, so in this case we have to convert milliliters to liters because concentration uses liters, not milliliters. So we do 0.2 moles divided by 1 liter. That's what 0.200 M is. Right, and then we know since we have 0.06 liters of that, and we know it's 0.2 moles of H2SO4 reacting for every 1 liter of it, we can convert it to moles that way. So that's a new type of conversion, but it's the same thing. You explore concentration in more depth in further units, especially in acids and bases and when you deal with a pH scale. But for now, you don't need to know too much about it. Last question. What mass of water can be produced from the reaction of 2 grams of H2 and 10 grams of O2 according to the reaction 2H2 plus O2 yields 2H2O? I actually wrote this on the back as well, just so that I have more space, because this question does require a bit more space. Now, in this question, we deal with something called a limiting reagent. In a chemical reaction, the reactants combine in a specific ratio. If they don't, one of the reactants will have some left over. That is the case for this type of question here. We will have some reactant have leftover of that substance. So in this case, we're trying to figure out, well, actually, we have the reaction, so that's a nice start. So now we want to figure out how many moles of each we have. So we know we have 2 grams H2, 2 G of H2, and then we have 10 grams of O2. Let's convert that to moles right there. So 1 mole of H2 per the atomic mass is 1.01, but it's H2 because it's diatomic, so that should be 2.02 grams of H2, which should give us 0.990 moles of H2. With oxygen, also diatomic, so the atomic mass is 16 times 2, which is 32, so 1 mole of O2 per 32.0 grams of O2. I forgot to cancel those units out. That'll give us the moles of O2 reacting, which is 0.313 moles of O2. So these are the amounts of each reacting. So we don't know how much water can be produced, but we're trying to figure that out based on how many moles of each we have. So to make this easier, I like doing something where I draw a table. So reactant, moles that we have, moles needed, as well as which one's excess and which one's limiting. So I want to do that with each element in this reaction. So we have H2, and then we have O2. So we know that, well, that is the reactant. So for moles of H2, we know we have 0.990, and for O2, we have 0.313. To figure out moles needed, we want to be using the mole ratio here. So we know we have 0.990 moles of H2, and then we're gonna use the equation to convert to moles of O2. So we have 1 mole of O2, because we look at this equation, reacting with 2 moles of H2. Those units will cancel. This will give us 0.495 moles of O2 needed. So 0.495 mole. Oh! So we have this many moles, but we need this many. So we know that this is a limiting reagent because we don't have enough of it to react in this reaction. We can do the same thing with hydrogen. So we have 0.313 moles of O2, and then we have 2 moles of H2 reacting for 1 mole of O2. Those units will cancel out, which should give us 0.626 moles of H2. So we have 0.626 mole. So we have 0.990, but we need 0.626, so we have more than we need, so we have an excess amount of this. But in this case, we can't use more than what we have. So we're gonna have to be using this amount. Basically what this table was just determining which of the elements in the reaction was limiting and which one we had an excess amount of. We obviously have to go with which one's limiting because we can't use what we have. We can't use more of what we already have. So in the actual problem, we're gonna have to be using the amount of moles of oxygen. So we have 0.313 moles of O2. And then if we look at the reaction, coefficient of water is 2, coefficient of oxygen is 1. So we know we have 2 moles of H2O reacting with 1 mole of O2. So that should give us moles of water. And then the molar mass of water, which I've gone over a few times before. I just memorized it to be 18.02 grams per mole of H2O, because H is 1.01, but there's two of them, so that's 2.02, and then oxygen 16. And then 1 mole of H2O per that amount. Type that into our calculator, and that should give us 11.3 grams of H2O. So we have 11.3 grams of water that can be produced if we have that amount of grams of each hydrogen and oxygen. Well, that's it, Johnny. That's all there is to stoichiometry. It's really not hard. You just take the moles and the mole concept and use that as the foundation to your calculations. Now, pop quiz. What two things are needed in order for a calculation to be done in stoichiometry? We need an equation that's balanced, as well as moles used to go from one chemical to another based on that balanced equation. Very good. Very good. I can see you've been paying attention, Johnny. I'm proud of you. Because you fell asleep in class, but you're definitely making up for it. Well, you know what? You've already done a big chunk of what you've missed. Come in again tomorrow, and we're going to learn about some equilibrium. Well, bell's going to ring soon, so take care, and have a great rest of your day.